Okay, so we only have 15 minutes per video, so once we get to that point, I'll stop and then move on to the next video. But as you read in your notes, maybe even the book, we can set up a standing wave on a string or a column of air. So this lab is going to be about setting it up in an air, in a tube or a pipe, but you do know that you can set up conditions that give rise to something known as a standing wave, where there's parts that that the string is hardly moving at all. Those are nodes. Other regions where the string experiences a large displacement, those are the antinodes. And we're going to look at some of those, and you might want to have your note packet open as we go through this. You shouldn't have to print this out, but I will put it in the lab. You could probably just go through the videos as you're trying to write the lab report. All right, so some objectives in this are going to be to take some data, which of course we can't really take up some data, but we're going to take some data like we're setting up wave patterns in a column in an open-ended and a closed-ended tube. And we're also going to determine the relationship between tube length and wavelength, and you have that in your notes. I think it's slide 28, I believe. And even though sound waves are longitudinal waves, we're going to use a transverse wave pattern to describe the nodes and antinodes because we can see those better. So we're going to draw it like this, okay, or see the data like this, even though the energy is moving perpendicular and the sound waves are really also moving perpendicular, but that's how we're going to look at it. And then we're going to determine the sound or speed of sound in air at a certain temperature. So we would have this set of materials, and this is what we would do here. Go on here. All right, so for the first thing, what we're going to do is we would take a pipe, PVC pipe, and we would smack it with just a finger. We would have it so that it's open. We'd create a sound, but there'd be an opening here and here. So this is going to be our open pipe. And then the second thing you do is take our palm and kind of hit the palm at the end of that, and we would create a closed on one end tube. And you might wonder, well, how would that tone of sound compare to the one that's produced earlier? And through calculations, we're going to show this, but you'd expect it to have a lower pitch. All right. So as we look at this, we know that we can have a standard wave, and we have our fundamental vibration in a string. And so looking at your notes here, you can see that that is half of a wavelength. Because we would start here, our equilibrium point, go like that, and then like that, and that would be our full if we were to do an entire wavelength. So we can see if we have a string, and so if this were a violin, this would be, you know, the string that's attached here, and this might be your finger as you put it down, and then you'd set up that resonance there. This would be the areas where we have nodes. And then this large part right here would be the antinode. But we are, again, we're going to be doing more of the air setup. And so what we're going to find here is that we have these compressions or condensations, I believe I referred to them in our notes, and rarefactions. And so we have this area here where it's condensed or compressed, and this area that isn't so much, because this air is moving like this, and it's transferring that energy, causing a disturbance, areas of high and low pressure, as we can see. So these are transverse waves, and that's how we're going to interpret those. So let's go ahead and just take a look at what you're going to start with. So I will label everything that you need to do as we go through here. So what I need you to do here in your lab report, so to speak, and you don't have to do an introduction or data and all that stuff. I'll just show you exactly what you need to do. The first thing that you want to do is to sketch the waveform for a fundamental mode, for air in an open tube. So again, if you want to look at slide 28, or you can just Google it too, but slide 28, go ahead and sketch it for an open tube on both ends. So we're going to call this number 1. Doing that sketch will be A. And then answer the question, how does the wavelength of the standing wave compare to the length of the tube? So again, you're going to get that. I would like you to go ahead and identify, let's call that C, a node and antinode. Okay, so just label that as number 1, A, B, and C. All right. As we go down here, let's see here. I don't know if I can do that. Nope, not let me. All right, I'll have to erase that, but you can go back. All right, so our standing waves in a column of air procedure, what we're going to do is to measure the temperature, and that temperature probe on there, you could measure the temperature. Let's assume we're at 25 degrees Celsius. All right, we're going to set our data collection up. We're going to get a PVC pipe, and the pipe length is going to be 0.40 meters, and its diameter is going to be 0.022 meters. Right? And we're going to put a microphone on the clamp, as you see the picture below. And you're going to start data collection. And you're going to smack it with one finger, creating a sound but not closing this end, so you have a pipe open at both ends. All right, your graph will show you sinusoidal form, a wave, and then you would run it 2 more times and store each one. You'd repeat it, except this time use your palm to strike the end of the tube, and this action essentially seals it off, so you have a tube that's closed on one end, but you've also created a sound. All right, so what we have to do now is take our data, and so of course you're going to need to have some data, and we're going to switch over to that, and take a look at what would be good to evaluate. So let me go find that. All right, so the first thing we're going to look at is this data that has come about for the pipe open at both ends. And the data that you need here, we're going to take one crest here. We're going to go 1, 2, 3, 4, 5. So we tap and drag, you know how that goes. And what we find down here, and of course cam scanner, you can't, that's over there, but the time that when you tap and drag, this is the time from here to here. So you could look down here and try to estimate, but it just gives it to you. So our data is going to be 0.01283 seconds. Now that's divided by 5 cycles. Okay, so when you do that, it's going to be 0.00257 seconds per 1 cycle. Okay, now frequency is cycles per second. So what I'm going to do is flip that, and I'm going to go 1 divided by that, and the reciprocal should be 389 hertz. Okay? All right, so record that, and then I'm going to open up the second graph that you get here. And this graph is amplitude versus frequency, and what we see here is a high point is about 390 hertz. So that agrees pretty much. It's a little over 390. That one is 389. So what we're going to go here is an average of those two. We're looking at about 390 hertz for the fundamental, the first harmonic, for a tube or a pipe open at both ends. Okay. Now, we could repeat this for the tube that's closed on one end, and we could look at that data, but I'm just going to give it to you. It is going to be 213 hertz. That's not from this graph, it's from a different one. This is going to be the fundamental on a tube closed at one end. And then we're going to just go ahead and compare those. And if we compare those, and this is the second thing that you'd have to do, so this would be our number 2 here. Just state the data from both graphs of this. So the last graph, just name the graph, and then talk about this graph, and talk about the fact that they're both about 390 hertz. And that's the conclusion I came to. And then for the pipe that's open only at one end, this was repeated and we got 213 hertz. All right. I guess we could make that number 3. All right, so that'll be number 3. Now, I would like you just to compare those two, and this is around 400, this around 200. So it's about half of the frequency. The tube closed at one end is about half the frequency of the tube open at both ends. So just make a note of that under number 3 when you compare the two. Compare open and closed, okay? And you'll see that the open at both ends is about twice the frequency of the one that's closed at one end. So just to make those observations, because that's pretty much all we can do. All right, so as we go through, there's a couple of other things we need to do here. So let's go back to the actual lab, which is here somewhere. Yeah. Nope. Did I just close that?